28th July 1944, 11,000 feet above the Dutch-German border. A formation of 8 Focke-Wulf FW-190s closes on what appears to be a solitary Republic P-47 Thunderbolt, separated from its squadron and seemingly vulnerable. The German flight leader, Oberleutnant Klaus Meertusch, veteran of 72 confirmed victories, signals his Schwarm to tighten formation. The Americans have been predictable lately, their heavy fighters trading maneuverability for firepower, lumbering through the sky like armored carriages. This one appears to be climbing away, a standard defensive posture. Meertusch drops his left wing and begins his attack run, the supercharger of his BMW 801 engine screaming as he pushes forward on the throttle. At 400 meters, well within range, he depresses the firing button. Nothing happens. His wingman reports the same. All 8 FW-190s are experiencing identical weapon failures. In the cockpit of the P-47, Captain Robert S. Johnson keeps his aircraft in a gentle climb, his right hand resting on a peculiar switch that shouldn't exist on a Thunderbolt. He hasn't fired a shot. He hasn't needed to. The Germans break formation in confusion, diving away, frantically cycling their electrical systems. By the time they've diagnosed the problem and reset their weapon circuits, the lone American has vanished into a convenient cloud bank. Meertusch lands at Dortmund 30 minutes later, furious and baffled. His armorer finds nothing wrong with any of the aircraft. The guns test perfectly on the ground. In his after-action report, Meertusch writes a single word in capital letters: Hexerei. Witchcraft. What Meertusch and his pilots had encountered was AN/APT-1, a device so simple in concept, yet so devastating in application, that Allied air commanders initially dismissed it as technically impossible. The modification weighed just 18 pounds, fitted into the radio compartment of a standard fighter, and required no external aerials or visible alterations to the aircraft's profile. Yet it rendered enemy fighters defenseless at ranges where visual identification remained impossible. The Luftwaffe called it the Zaubergerät, the magic device. The Americans, with characteristic directness, called it the jammer. History would remember it as one of the war's most effective electronic countermeasures, a weapon that achieved strategic results not through destruction, but through denial. The challenge facing Allied fighter forces in mid-1944 was simultaneously mundane and existential. German fighters, though increasingly outnumbered, maintained a distressing ability to inflict casualties. The mathematics were brutal. An attacking FW-190 or BF-109 needed just 2 to 3 seconds of firing opportunity to destroy an American heavy bomber. The standard MG-151/20 cannon, firing at 750 rounds per minute, could put 12 20mm shells into a target in that brief window. Against the unarmored rear fuselage of a B-17, where fuel lines and control cables ran exposed, this was invariably fatal. Allied fighters provided escort, certainly, but the sky over Germany was vast and the Germans excelled at identifying momentary gaps in coverage. Between January and May 1944, the 8th Air Force lost 2,088 heavy bombers to fighter attack. That represented not merely aircraft, but 20,880 highly trained aircrew, each man requiring 18 months and $90,000 to produce. The arithmetic was unsustainable. Fighter pilots reported a consistent frustration. They could see the enemy, could maneuver into firing position, could even occasionally surprise German formations, but securing kills proved maddeningly difficult. The FW-190 in particular demonstrated exceptional diving performance and could disengage from combat almost at will. When American fighters closed to firing range, German pilots simply pushed their control columns forward and vanished earthward, their radial engines and sturdy airframes tolerating accelerations that would tear the wings from a Mustang. By the time Allied pilots cautiously followed, wary of high-speed compressibility, the Germans had leveled out and disappeared into ground clutter. combat film analysis revealed a depressing pattern. For every 1,000 rounds of .50 caliber ammunition expended, American fighters achieved an average of 1.2 confirmed kills. Against experienced Luftwaffe pilots, this ratio deteriorated further. Something had to change. The solution emerged not from aeronautical engineering, but from an entirely different field. Dr. Harold Beveridge, a radio propagation specialist at RCA's Rocky Point Laboratory, had spent the 1930s studying atmospheric interference in commercial broadcasting. His particular expertise lay in understanding how electromagnetic radiation affected electronic circuits at specific frequencies. In early 1944, military intelligence provided Beveridge with a curious piece of equipment: the electrical firing mechanism from a captured FW-190A6. The German system was remarkably sophisticated, employing a motorized gun charger powered by a 28-volt DC circuit with electromagnetic relays controlling firing sequence. Each weapon system operated on identical frequencies, standardized across the Luftwaffe to simplify maintenance and logistics. This standardization, sensible from a manufacturing perspective, represented a profound vulnerability. Beveridge recognized immediately what others had missed. The German firing circuit employed shock-sensitive relays that required precise voltage timing to function. Introduce electromagnetic interference at the correct frequency and amplitude, and those relays would trip prematurely, interrupting the firing sequence without causing permanent damage. The affected pilot would experience what appeared to be random weapon failure. More crucially, the effect was instantaneous and occurred before the German pilot depressed his firing button. The circuit disruption happened the moment the jamming signal reached the relay, which meant Allied fighters could theoretically disable enemy weapons before hostile intent even translated into action. The implications staggered everyone who understood them. This wasn't electronic warfare as then conceived, which focused on disrupting radar and communications. This was something altogether more intimate, reaching into an enemy cockpit and removing his ability to kill. Development proceeded with extraordinary urgency. Beveridge's team, expanded to include specialists from Bell Laboratories and the Army Signal Corps, faced a deceptively simple challenge: build a transmitter small enough to fit into a fighter aircraft, powerful enough to affect circuits at 400 meters, yet not so powerful that it interfered with the carrying aircraft's own systems. The frequency range was narrow, between 38 and 42 MHz, coinciding precisely with the FW-190's firing control band. Too low, and the signal wouldn't propagate efficiently. Too high, and it would scatter uselessly. The power requirement was equally critical. Initial calculations suggested 50 watts would suffice, but field trials demonstrated that atmospheric attenuation, aircraft vibration, and combat maneuvering reduced effective range dramatically. The final specification demanded 85 watts continuous output, which in 1944 required thermionic valves cooled by forced air ventilation. The AN/APT-1 that emerged from this development process resembled a large wireless set. The main unit measured 18 inches long, 8 inches wide, and 6 inches deep, housed in a magnesium alloy case with rubber shock mounts. Inside, 12 vacuum tubes generated the jamming signal through a heterodyne oscillator circuit that produced remarkable frequency stability despite temperature variations and combat acceleration. The antenna was deliberately crude, a simple quarter-wave whip aerial, 1.9 meters long, that could be retrofitted to the existing radio aerial mount on most American fighters. Power consumption drew 12 amperes from the aircraft's 28-volt electrical system, manageable for the robust generators fitted to Thunderbolts and Mustangs, but marginal for older types. Total installation weight, including cabling and the control panel, came to 18.4 pounds, a trivial penalty for a fighter already burdened with ammunition and fuel. The human element of this story centers on Beveridge but extends to a supporting cast of engineers who worked 18-hour days through the spring of 1944, Lieutenant Colonel Francis L. Moseley, assigned by the Army Air Forces to oversee the project, became the device's principal advocate within the military bureaucracy. Moseley had flown P-38s over North Africa and understood viscerally the frustration of watching German fighters escape. He recognized that AN/APT-1 didn't need to destroy enemy aircraft. It merely needed to prevent them from destroying Allied ones. In a meeting at Wright Field in April 1944, Moseley presented a brutal calculation. If the device prevented just 10% of German firing opportunities, it would save approximately 200 heavy bombers per month. At $250,000 per B-17, this represented $50 million in preserved assets, not counting the irreplaceable aircrew. The cost of equipping every 8th Air Force fighter with AN/APT-1 was $340,000. The arithmetic convinced even the skeptics. Manufacturing began in May 1944 at RCA's Camden plant, where workers accustomed to building entertainment radios found themselves assembling classified military equipment under armed guard. Production schedules demanded 150 units per week, an ambitious target that required round-the-clock shifts and priority allocation of vacuum tubes, which remained in chronic shortage. Each unit underwent 3 separate testing stages: bench testing for frequency accuracy, environmental testing in a thermal chamber that cycled between -40 and +60 degrees Celsius, and finally installation testing in a P-47 fuselage mock-up, subjected to vibration loads simulating combat maneuvering. Rejection rates hovered around 12%, primarily due to valve failures and intermittent solder joints. By late June, 380 units had been delivered to the Modification Centre at Burton Wood, near Liverpool, where they awaited installation in operational aircraft. The first squadron to receive AN/APT-1 was the 56th Fighter Group, equipped with P-47Ds and based at Boxted in Essex. Security surrounding the modification was extraordinary. Pilots received no advance briefing. Ground crews were told only that the equipment was experimental radio apparatus and threatened with courts-martial for discussing it. Installation occurred overnight on selected aircraft, distinguished only by a small red star painted beneath the cockpit. On 2 July 1944, 12 modified Thunderbolts took off on a fighter sweep over the Netherlands. Flight leaders carried sealed orders to be opened at 20,000 feet. When they did, the instructions were startlingly simple. Locate enemy fighters, close to within 500 meters, activate the device using the unmarked switch on the throttle quadrant, observe results, do not mention this equipment on any radio frequency. Captain Walker Mahurin, leading the second flight, encountered a staffel of BF-109G6S north of Arnhem at 15:30 hours. Following his orders, he closed to 450 meters, flipped the switch, and watched. The results exceeded even optimistic predictions. All 4 German fighters simultaneously broke formation, entering violent evasive maneuvers as their pilots attempted to clear weapon jams that weren't actually jams, but rather electrical failures their training had never anticipated. Mahurin, expecting to follow with gunfire, found himself almost disappointed. The Germans scattered so completely that pursuit became unnecessary. 2 of the Messerschmitts collided during their panic maneuvers, a bonus kill attributed entirely to confusion. Post-mission analysis at Boxted was conducted behind closed doors. The 56th's commanding officer, Colonel Hubert Zemke, prohibited any written records. Pilots were instructed to report weapon malfunctions among enemy aircraft as coincidental equipment failure, nothing more. The secret held for precisely 6 weeks. During that period, AN/APT-1 equipped fighters flew 847 sorties and encountered Luftwaffe aircraft on 203 occasions. German pilots reported weapon failures in 167 of those encounters, a staggering 82% incidence rate. More significantly, those failures occurred at crucial moments, during gunnery approaches, bounce attacks from altitude, and stern chases where German fighters would normally hold every advantage. Allied bomber losses to fighter attack dropped by 41% during July and August, a decline that analysts initially attributed to reduced Luftwaffe strength, until the correlation with jammer-equipped escort became undeniable. The modification's effectiveness varied by aircraft type. Against the FW-190, which employed the most susceptible firing system, success rates approached 95%. The Bf-109's slightly different electrical architecture proved less vulnerable, though still affected at close range. Twin-engine fighters like the Bf-110 showed almost complete immunity, their redundant electrical systems and different relay designs defeating the narrow-band jamming. German awareness came gradually, then all at once. Luftwaffe maintenance records from July 1944 show a mysterious spike in reported electrical failures, initially dismissed as deteriorating quality control in component manufacture. By mid-August, however, the pattern had become impossible to ignore. Failures occurred exclusively during combat, never during routine patrols or ground testing. They affected all aircraft in formation simultaneously, suggesting external causation rather than internal fault. On the 17th of August, Hauptmann Emil Clade of JG-3 reported that his weapon failure coincided precisely with an American fighter closing to within 300 meters, an observation repeated by 3 other pilots in subsequent debriefings. The Luftwaffe's Technical Intelligence Service, already stretched thin, assigned a low priority to the investigation. They assumed, not unreasonably, that the Americans had developed some form of electromagnetic artillery designed to disable electrical systems, possibly involving focused radio beams or directed energy. The actual mechanism, a simple continuous wave jammer exploiting standardized relay frequencies, eluded German analysis for months. The countermeasures, when they finally arrived, were characteristically German in their thoroughness and tragically late in their deployment. Focke-Wulf's engineering team redesigned the FW-190's firing circuit to operate on variable frequencies selected by a cockpit-mounted dial, similar to radio tuning. This modification, designated Umrüstbausatz 20, began reaching frontline units in November 1944, but production delays and the general collapse of German logistics meant fewer than 200 aircraft received the upgrade before the war ended. Messerschmitt pursued a different approach, developing a purely mechanical backup firing system that bypassed electrical circuits entirely. Pilots could manually cock their weapons using a hand-operated lever and fire through a pneumatic release, primitive but immune to jamming. This system weighed 32 pounds and reduced ammunition capacity by 15%, penalties that proved acceptable given the alternative. The backup system entered production in January 1945 and saw limited service during the final months of the war. Allied intelligence monitored these countermeasures with considerable interest. Captured FW-190F9S, examined in March 1945, revealed the frequency-variable firing system, which prompted immediate concern. The solution arrived from an unexpected quarter. Engineers at the Naval Research Laboratory developed a swept-frequency jammer, the AN/APT2, that cycled through the entire 38 to 42 MHz band in under 2 seconds. This rendered frequency variation useless, though at the cost of increased power consumption and reduced effective range. Only 67 AN/APT-2 units reached operational squadrons before VE Day, insufficient to assess their combat effectiveness. The British, meanwhile, had pursued parallel development. Their Type 91 jammer, designed to affect the Bf-109's firing system, operated at different frequencies and achieved modest success in trials. Operational deployment was limited to specialist aircraft, flown by the Telecommunications Research Establishment, and British pilots reported mixed results. The Type 91 suffered from reliability issues, particularly valve failures in cold conditions at high altitude, and was withdrawn from service in February 1945. The Pacific Theater presented entirely different challenges. Japanese aircraft employed mechanical firing systems almost universally, making electromagnetic jamming ineffective. A handful of AN/APT-1 units, shipped to 8th Air Force units in the Marianas, saw no combat use and were eventually removed to reduce weight, the mountings repurposed for additional fuel tanks. The technology found an unexpected second life against Japanese shipping, where coastal defense vessels employed German-supplied anti-aircraft weapons with electrical firing circuits identical to those in the FW-190. Navy fighters equipped with AN/APT-1 reported several instances of coastal batteries falling silent during strafing runs, though distinguishing genuine jamming effects from simple destruction proved impossible. Post-war analysis suggested these successes were coincidental, the result of suppressive fire rather than electronic interference, but the possibility remains intriguing. Statistical assessment of AN/APT-1's impact requires careful contextualization. During the 6 months of widest deployment, July through December 1944, jammer-equipped fighters participated in approximately 4,200 sorties over occupied Europe. Luftwaffe aircraft encountered during these missions reported weapon failures at rates 67% higher than the preceding 6-month period. Heavy bomber losses attributable to fighter attack declined by 38% during the same interval, though this figure reflects multiple factors including diminishing Luftwaffe strength, improved Allied tactics, and the increasing prevalence of long-range escort fighters. Isolating the jammer's specific contribution proves statistically challenging. Conservative estimates suggest AN/APT-1 directly prevented between 180 and 250 bomber losses, representing roughly 1,800 to 2,500 aircrew lives. The device achieved this without firing a shot, without adding visible weight or drag to Allied fighters, and at a unit cost equivalent to 600 rounds of .50 caliber ammunition. The psychological impact defied quantification, but emerged clearly in German documents. Luftwaffe pilots' combat reports from autumn 1944 frequently mention hesitation during gunnery approaches, with experienced pilots describing a moment of uncertainty before pressing the firing button, wondering whether their weapons would function. This split-second doubt, multiplied across hundreds of engagements, degraded German combat effectiveness in ways that transcended mechanical failure. Fighter pilots operate in an environment where confidence and timing mean everything. Introduce uncertainty into that equation, and performance collapses. Several German aces, including Hans-Joachim Marseille's former wingmen now serving on the Western Front, reported in post-war interviews that weapon reliability concerns caused them to abandon otherwise favorable attack positions. The fear of experiencing failure at the critical moment proved as debilitating as the failure itself. The technology's legacy extended well beyond 1945. Post-war electronic warfare doctrine incorporated lessons from AN/APT-1, particularly the principle that denying an adversary's ability to employ weapons could prove as valuable as destroying those weapons directly. The Korean War saw deployment of AN/APT-3, an improved jammer designed to disrupt MiG-15 gun systems, though Soviet electrical architecture proved less vulnerable than German designs, and results disappointed. Vietnam-era Wild Weasel aircraft carried descendants of Beveridge's original concept, scaled up to target surface-to-air missile systems rather than individual fighters. Modern electronic countermeasures suites, standard equipment on all combat aircraft, trace their conceptual lineage directly to that first crude jammer fitted into P-47 radio compartments in 1944. Physical examples of AN/APT-1 remain remarkably rare. Only 3 confirmed units survive in museum collections, one at the Smithsonian's National Air and Space Museum storage facility, still installed in a P-47D fuselage section, another at the Imperial War Museum, Duxford, displayed alongside a captured FW-190 to illustrate the cat-and-mouse dynamic, and a third at the United States Air Force Museum in Dayton, partially disassembled to show internal components. A fourth unit, reportedly in private hands, surfaced at auction in 2019 but disappeared before authentication. The scarcity reflects post-war scrapping programs that treated the jammers as obsolete radio equipment rather than historically significant artifacts. Most were unceremoniously removed during demobilization and recycled for their vacuum tubes and magnesium housings, both materials in short supply during reconstruction. Recent scholarship has reassessed AN/APT, one's significance within the broader context of electronic warfare evolution. Dr. Christina Goulter's 2018 study on RAF electronic countermeasures argued that the jammer represented a pivotal moment when electromagnetic spectrum control transitioned from defensive radar jamming to offensive weapons denial. The device demonstrated that electromagnetic radiation could serve as a weapon in its own right, not merely a tool for blinding sensors, but for reaching into enemy systems and inducing critical failures at precisely chosen moments. This conceptual leap, Goulter argues, prefigured modern cyber warfare more accurately than any other World War II technology. The jammer didn't destroy anything. It simply prevented destruction by others, a profoundly different approach to achieving air superiority. The story of AN/APT-1 also illuminates the complex relationship between technological sophistication and battlefield effectiveness. The German firing system it exploited represented advanced electrical engineering, a triumph of standardization and reliability that served the Luftwaffe superbly in every context, except the one that emerged in 1944. The Allied jammer, by contrast, was almost primitive, a radio transmitter operating on a fixed frequency, requiring no exotic materials or revolutionary scientific insights. What it demanded was recognition of opportunity, the ability to see vulnerability where others saw strength. Beveridge's genius lay not in inventing new physics, but in applying existing knowledge to an unconventional target. The lesson transcends its immediate historical context. Sometimes the most effective solutions emerge not from advancing technology's cutting edge, but from understanding current technology's limitations. The modification that shocked the Luftwaffe ultimately relied on an elegant inversion. German engineers had created a highly efficient, standardized electrical system that maximized reliability and simplified logistics. Allied engineers recognized that this very standardization created a single point of failure exploitable through well-understood electromagnetic principles. The result was a weapon that worked not by being more powerful or more sophisticated than its target, but by being more cleverly applied. In the vast technological competition of the Second World War, where radar fought radar and armor countered armor, sometimes the decisive edge came from recognizing that the enemy's strength, pushed just slightly beyond its intended parameters, could become catastrophic weakness. An 18-pound box and 85 watts of radio transmission proved sufficient to transform that recognition into reality, one confused Luftwaffe pilot at a time.